I can first record. Uh, so our speaker has allowed like to have short question during the talk. So if you have any question, don't be afraid to unmute yourself, or you can always leave the question in the Zoom chat as well. And so we are happy to have Dr. Fernando Pinero González from University of Puerto Rico doing a crash course in coding theory. Fernando.
All right. Uh, I would like to thank the organizers for this opportunity. I'm really very happy to be here. Yeah. So, I prepared a crash course in coding theory. I have some things I would like you to learn about coding theory, but I'm a pretty chill guy. If you ask many questions and our conversation is derailed, well, as long as you learn at least one thing of coding theory, I'll be very happy. So let me just share my screen. Let me just share all of it. All right. Um, all right. I believe everybody can see my slides.
Yes.
Yes. All right. So, hello everyone. I am Fernando Pinero González, and I am an associate professor at the University of Puerto Rico in Ponce. Then I will just talk about some, let's say, some fundamental things in coding theory, but I believe I have some, let's say, encoding, decoding algorithms. So I think you can at least get a little bit of coding. You can take a bit of coding theory home. If you have any questions or comments, feel free to share. So let's begin.
I
So,
just want to interrupt. I think you have like a black thing. The Zoom is like also blocking some of the screen sharing.
oh,
Just
you mean this?
yeah, like we this.
Okay. Uh, is
Okay,
it better now?
yeah, it's better a little bit. I'm not sure if it's internet. I just want to point out.
Oh, all right, all right.
Yeah, I think it's fine. It doesn't block the main body, I guess.
Very well. All right. So I'll just give you a brief introduction to coding theory. I will talk about two classes of code. These are one of the best known, the most fundamentals. And then, since I'm running an REU in 2025, I'll take the chance and at least talk about some of the coding theory projects I have in mind to run. All right. So Claude Shannon was a mathematician from Bell Labs, and he, in about, I think, 1948, developed the, let's say, essay slash manuscript, a mathematical theory of communication, in which he lays the foundation of what is known today as coding theory. In particular, the mathematical foundations you need in order to make digital communications reliable. So he sets everything in a more or less a more formal way, and he says the following: the fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected at another point. But in particular, what he means, he has in mind what is known as the Shannon-Weaver communication model. There's an information source, in this case, it's M in the red box, and this is what the source wants to send to the destination. So this has to be prepared to be sent. So he encodes the message M into a code word C, where a code word C is selected from a collection of possible code words in such a way that M and C are in a one-to-one correspondence. Yeah. So for example, you can think of, let's say you want to send the word bone. So you type it on your computer sends, encodes it to ASCII into zeros and ones. It's sent through the internet as a binary signal. Yeah. So that's what encoding means. So he takes the code word C. That's the encoded code word corresponding to the message. It's encoded to a signal. It's sending an antenna or CD, or it's sent as something you write in your hard drive, yeah, and then you retrieve it at a later date. So the thing is that the physical act of sending something will introduce noise. And this is here from my red E. So the receiver, he doesn't receive the original code word. He will receive, let's say, C prime, which is the original code word, plus the errors that came from the noise source. And now the receiver has the task to determine, to recover, to decode what was supposed to be the original message, knowing that he received a code word with some noise. And in this case, I put that the destination recovered M as well, but this may or may not be the case. I mean, if you have too many noise, such a thing may not even be possible. So this is the Shannon-Weaver communication model, yeah? So, but in that same, foundational work, he established a theoretical code. He said, your channel has some sort of capacity, and he said you can send information at any rate up to what the channel can handle, and you can encode information in such a way that you can recover information with an error rate as low as you want. If your channel has a certain capacity rate, you cannot transmit information at a higher rate than that. So he said it's possible to get as close as you like to the capacity of the channel and encode information in such a way that you can make the information as reliable as you want. However, this was an existential proof. Yeah, and mathematicians are really fond of existential proofs. But then, if I give you a collection of messages, he doesn't say how one can construct code words. If you have a collection of code words to be sent through a channel, you don't know how to map the message that you want to send into the appropriate code word. And if you received a code word, or even if you received a code word with errors, you don't know how to recover the original thing. So coding theory is an area developing ever since Shannon's foundational essay. And it consists of finding, let's say, mathematical objects or mathematical ideas to build and to find good codes which can make this happen. So in this talk, I have some examples to see how this can be achieved. So I will present some of the classic codes. Yeah. So just some notions to, let's see, how can I say this, get you settled into the idea. In general, a code in coding theory, it's something that has a very, very, very little structure. So the alphabet of the code is just a set of symbols, and here it's denoted by sigma. A code over sigma of length n is just a bunch of n tuples. I mean, no structure whatsoever. But if you make sigma a field and you make seed in red, instead of being a collection of tuples, if you make it a vector space, then actually this is known as a linear code, and you get many things by working with linear codes, but you do pay a price. I mean, it's not for free. If you look at constructions of codes, we can find non-linear codes which are better than what a linear code can be, but they're really hard to study. So now one of our benefits of defining a linear code is that we can really quantify how many code words a code has by the dimension. Yeah, so the dimension of the code is the dimension of the code as a linear space, or if it's just a collection, you just take the logarithm in base of the size of the alphabet. So, all right. Yeah. So, right. So I like this function. I mean, when I took topology quite a while ago, I was very happy to see that the distance function can be generalized. So a distance function is just a function from ordered pairs of a set into the real numbers, such that the function is non-negative. The only thing that evaluates to 0 is when two things are equal. The function is commutative or it's symmetric on its inputs, and it satisfies the triangle inequality. So there's many, many, many functions which satisfy this criteria. So for example, the Euclidean distance, this is the classical, Pythagorean distance you learn in pre-calculus. The Manhattan or the taxi cab distance, this is just the distance is the sum of the absolute values of the differences between positions. So the reason it's called the Manhattan distance is that if you're in a grid, this is the number of blocks you have to go to get from one point to the other. From one point to the other. The Levenshtein distance, this is used more, let's say, in DNA or RNA. This is the edit distance, or how many additions, additions, subtractions, substitutions you have to make from one DNA string to the other to get from one to the other. If you define distance as the shortest path between two vertices in a graph, this is a distance function. And the one of most interest for us, if you have two tuples of elements in sigma, the Hamming distance is simply the number of positions in which both tuples do not agree on. Yeah. All right. So if you have a code, the minimum distance, in coding theory, we will focus mainly on the Hamming distance. There's other codes. Sorry. There's other codes which can be defined with other distances, and they can also be really interesting to deal with. But yeah, but we don't. So if we have a code, the minimum distance is just the smallest distance between any two distinct code words. So basically, you look at all the code words, and however many positions any two of them have the least in common, that's the minimum distance of the code. If sigma is a field, then we're sure to have the 0 code word, and this gives us the Hamming weight of a vector, and it's just the number of non-zero coordinates. And if C is a linear code, or just a set closed under addition, then you don't need to check all the pairs to compute the minimum distance. It just suffices to compare any non-zero code word, compare it to 0. Yeah. And then if you have a code of length n, dimension k, and distance d, then we call it an NKD code. Okay, yeah. So this is just, so since these are the parameters which best describe the performance of a code with regard to the Shannon-Weaver model, so this is usually the parameters we use. But, recently there's other code parameters which are also of interest. Okay, so now if you remember that I said Shannon gave an existential proof for the existence of a very good linear code. Sorry, not linear, for a very good code. So then shortly after, Richard Hamming said, well, I can make a really awesome code using the binary field. So the way the binary Hamming code works is as follows. We have here on the screen three interlocking circles, and these circles define 7 regions. Yeah. So what you do is you place zeros and ones on each of the regions which are common. Yeah. So you take these 4 bits and you will think of the 4 bits as your message. And then you say, well, I'm going to add 3 more bits. I'm going to add 3 more zeros or ones such that each circle has an even number of ones. So now, since the top circle had 2 ones, you add a 0. Since the left circle had only 1, 1, you add a 1. And since the right circle only had 1, 1, now you have 2 1s, yeah? And that is your code. So you begin with 4 bits from the 4 common regions, and you add 3 more, yeah? So you encoded 4 binary digits into 7. And that's why it's a 7-4 code, yeah? All right, so what can we do with this thing? So for example, if everything is 0, then this is a valid code word. And you can think or you can pretend, for example, if you want to send information, you take your 4 original bits, you do this, put them in a circle and add the 3 positions, and you send that instead. So if you want to send the 000 message, you encode it into the 0000000 message, yeah, from 4 zeros to 7, and you send this. So now, errors will happen along the way, and now the receiver has received this. Yeah, he received a message which has 6 zeros and 1 1 in the way it's put here. Okay, so I have a question to the audience and see. Let's see. Can anyone identify what would the wrong position be? Well, all right. So if you look at the upper circle, it has no ones, so therefore it has an even number of zeros. The left circle has a single one, so therefore it has an odd number of zeros. And the right circle has no ones, so it has an even number of zeros. So we know that the bad position should be this one, yeah? So in this example, we know that the bad position is this one because the upper circle has only 1 1 and the left circle has only 1 1, yeah? But in this case, for example, both lower circles have an even number of ones. The upper circle has an odd number of ones, and this received word is decoded into this one. Yeah. So the circles are telling you how to recover or how to determine what would the original message have been, because we are establishing relations between the different positions. Yeah. Very well. If you want to be a bit more flexible, a fairly recent change in here, this is a binary code, it's zeros and ones, the way you compare things about things. Yeah, it's a bit is either on or off, but sometimes you don't know things with absolute certainty. Yeah. So what you could do here instead is that you could, instead of getting a 0 or 1, you have a probability of something being 0, and therefore a probability of something being 1. You still have the relation that everything in a circle is supposed to be, 0. But now, instead of just having zeros or ones, you know that each position has an idea on how likely they are to be either 1 or 0. So for example, in this case, the second, third, fourth, and fifth position are supposed to be 0, and that will be here the upper circle, yeah? So for example, if we put here that each position gives you the probability it thinks that it is 1, you can see here that this position, it really thinks it should be a 1, where everyone else really thinks they should be a 0. So what you do is that each circle will say, all right, by looking at what everyone thinks they should be a 1 or a 0, each circle will tell each of its positions what they should be. And each of the positions will consult with the circles they're in. And therefore, so basically everybody will check with their neighbors and they will update their own opinion on what their probability should be. So the circles tell everyone in the circle thinks you should be, you're very likely to be this 0 or 1. And then everyone checks their opinion contrasted to the circles they're in. So after one round, everyone kind of updates their probability. So in this case, we have 3 positions where they're really, really sure they're 0. And, before, the position on the second row in the right really thought it was a 1, but now it really, really believes it should be a 0. And the upper position is a bit more confused. But now we do this again, and now we can see basically pretty much everyone is sure that they should be 0s. Yeah. So, and then you say, well, this is close enough, and you decode this to the 0 code word. Yeah. So what should I mention here? So if you look at current methods in forward error correction, what the actual electrical engineers call coding theory, the way they encode information to protect it against errors. So they use something like this. So of course they call it LDPC codes. So basically they make many circles with many positions, and they do this sort of iteration back and forth. Yeah, it's extremely quick, and it gets the job done. Yeah. All right, moving on. Okay, so yeah, so as I mentioned, a linear code is actually a vector space over a field. So a field is just a ring in which you can add, subtract, multiply, and divide. And these are the classical examples, the rational numbers, the real numbers, the complex numbers. But, you don't need many elements to have a field. In fact, you only need 2. If you define addition and multiplication as above, yeah, then this is a field with 2 elements. And actually, when you learn a bit more about fields with a finite number of elements, you learn that this is essentially 1. So this is the field with 2 elements. And if you do the integers modulo p, where p is a prime, then this will also give you another field with p elements. Yeah. So why am I talking about fields all of a sudden? Yeah. Because if you have a field, you have matrices, you have vector spaces, and you have many awesome things. If you have a field F and you have an NKD code, if C is a linear code, then a generator matrix is any K by N matrix whose rows are a basis for C. If you look at its orthogonal complement, the set of vectors whose dot products are 0 with all code elements, then this is another code. Yeah. So one of the awesome things about having linear codes, even though you can think of them being a bit too structured, but if you have a linear code, you get another code for free, which is the dual code. Yeah. It's the set of all vectors in F to the N, which have dot products here. Yeah. And this gives you an additional way of defining codes. So you can define you can define your code words by either being elements from the row space of the generator matrix, or vectors who have dot product 0 with the generator matrix of its dual code. Yeah. And the really important thing, or the reason why I mentioned this, is because now if you put in symbols here, then you get this generator matrix. And so you have a fairly simple representation of the 743 binary Hamming code by a simple 4x7 binary matrix. Yeah. So by having linearity and by adding the algebraic relations or the algebraic structure from F2, then you can do a fair amount of linear algebra as well. Okay, moving on. Actually, I wanted to mention this. Yeah. So let me go back. The other benefit we have, if you look up here, I put in some parity check equations for C1 plus C3 plus C4 plus CCB. C6B, 0. Yeah. So that first equation here would correspond to this circle here. Yeah. So by using the binary field, then we can just represent codes by a bunch of linear equations. And we're really, 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 really good at solving linear equations. Yeah. Very well. So this is actually Hamming's first code example, and I believe this was used in the 50s to encode information back when computers were made of paper, when you had to punch holes to run a program. Then you could use the Hamming code to make sure that the punches you made actually were done, adequately. Yeah. So this was used in a computer even before the computer was made of electrons. Yeah. All right. So now for something completely different. Yeah. And the reason why I have this huge skip is because Reed-Solomon codes are another class of codes which have a really rich algebraic structure. And I mean, notwithstanding a finite field, you can basically, understand them with basically a bit of precalculus. If you take number theory and then you learn about finite fields or just mod p arithmetic, then you can actually work with these codes in earnest. Yeah. So how do Reed-Solomon codes work? Very simple. You take FQ, your favorite finite field with Q elements, and you take n elements of this field. You take k to be between 1 and n. So the Reed-Solomon code of length n and dimension k, you basically take all polynomials of degree less than k, evaluate them at all the points of L, and all those n tuples are your code words. That's your Reed-Solomon code, yeah. So basically, the Reed-Solomon code is comprised by the image of a polynomial function evaluated at a finite set of points. Yeah. So why is this awesome? I can state outright that this is an nk n minus k plus 1 code. And the proof outline is, well, we need to establish k independent vectors. Basically, if you take 1x squared up to x to the k minus 1, we need to establish all those evaluations are independent. But you also need to establish that any non-zero code word has at least n minus k non-zero positions. And the awesome part about this is that both are a straightforward application of the fundamental theorem of algebra. So for example, here, the degree of f is less than k, right? So the degree of f is at most k minus 1. So therefore, it has at most k minus 1 zeros. So it has at least n minus k plus 1 zeros. Yeah. So just by saying I will make a code by evaluating polynomials in a single variable over the elements of a finite field, I can already tell you what the length, dimension, and distance is using fairly elementary mathematical techniques. Yeah. So this is a really awesome detail of Reed-Solomon codes. Reed-Solomon codes were really big in the 90s and the early aughts. If you have a CD or a DVD, it was encoded using a Reed-Solomon code of length 255 and dimension usually 236 over the field of 256 elements. Currently, there are other codes which are sort of derived. And so there are a class of codes called BCH codes, which either are derived from or generalized Reed-Solomon codes. You can look at it either way. Reed-Solomon codes from BCH codes or BCH codes from Reed-Solomon codes. So it's a way to get the best of both worlds, having a small alphabet field, but the awesome structure of the Reed-Solomon code. So BCH codes are still used in practice. They have been surpassed by LDPC codes, but I mean, I love algebra, so I find it a wonderful excuse. So I love BCH codes as well. But I don't want to, let's say, get too far from this. So the other thing I really want to teach you would be, why are these codes so awesome? So if you have any NKD code, the singleton bound will tell you that the distance cannot be too large. In particular, yeah, the distance of an NKD code cannot be bigger than n minus k plus 1. And should you have equality in that case, you call this an MDS code, or a maximum distance separable code, because it has the best distance possible for the choice of n and k. So if you recall what I mentioned about a polynomial of degree at most k minus 1, having at most k minus 1 zeros, and therefore having at least n minus k plus 1 non-zero values in any set of n points in a finite field, then we establish that the Reed-Solomon code of length n on dimension k is actually an MDS code. So not only just taking monomials and polynomials in a single variable with a finite field give us a code in which we know the length, dimension, and minimum distance, these three things are the best possible. Just by using a fair bit of algebra, I fell in love with these codes, yeah, when I learned about these. But what really made these codes awesome is that they also have a way to recover the original message. Yeah. So you have your channel and you want to send 3 digits. You want to send the digits 2, 4, and 1. Yeah, you want to send the number, let's say 241. And this is a noisy channel. So in a sense, you suppose that you have a 20% error rate. Yeah. So when you send things in your channel, you 1 out of every 5 positions you send will be changed. Yeah. So if you send just the tuple 241, you have only an 80% chance each position is correct, and therefore the triple will be correct only about half of the time. Oh, this is horrid, yeah? So how can we make this happen? How can we fix this? Well, the first thing you learn, or one of the basic codes, is repetition codes, yeah? If your error rate is, I mean, not too bad, so you just treat it like you just repeat everything 3 times, and instead of sending 2, 4, 1, you said 2, 2, 2, 4, 4, 4, 1, 1, 1. And then if you do this, then your error rate for your triple, it's improved. So now the probability the person will receive your original triple correctly is improved from 51% to 71%. But now it's horrid. It's bad. The information rate is bad. Because before, you just had to send one number for each information bit you wanted to send, but now you have to send everything 3 times. So out of every 3 things you send, only one has information. The other 2 are just repetitions of whatever came. So you have lost your, let's say, communication efficiency. Yeah, because now out of every 3 positions you send, only one will give you what you need. So you have lost a 66% of the information rate. So what can we do? So if you have a field which has 5 elements, let's call them -1, 1, 0, 1, and 2, yeah? So what you do is you map the message 2 for 1 to the polynomial 2 plus 4x plus x squared, yeah? And so know that the 3 numbers are the coefficients of the polynomial. But you're not going to send that polynomial. You will evaluate your polynomial of degree 2 at the 5 points you have chosen, and you send the image under this evaluation map. So you send -2, -1, 4, 7, and 14, the evaluation of the polynomial at the 4 points. Now, to send the 3 information bits, you need 5 digits. So instead of losing 66%, you only have an information loss of 40%. And now, since you can do some clever tricks, and if whenever you have a single error, you can always be sure to correct it, you can always determine what the correct result was at least 33% of the time. And then you can wonder, why would I use this thing? If I do this, I have a worse improvement at a worse cost, yeah, because I have less information for a less rate. So it seems that Reed-Solomon codes are the be-all end-all codes in coding theory, and that's what we hoped. But you have a price to pay, yeah, which is up here. I said take a field with at least 5 elements. So your field size has to be at least the length of the code. And therefore, that will make your code operations very, very complicated. You can do certain tricks, right? Reed-Solomon codes are defined essentially by points of a line. If you like algebra, you know that if you work in the plane, you have circles, parabolas, cubic forms, yeah? So for example, if you evaluate all polynomials into variables in degree at most 2, at, let's say, enough points in a circle, then the polynomial will define a polynomial curve of degree 2 or less. And any polynomial of degree 2 or less, which is not the circle, will have at most only 4 points of the circle. Yeah. So therefore, knowing that a curve of degree 2 and a circle have only at most 4 points in common will give you information about the corresponding code given by evaluating, let's say, functions in a circle. And this is the idea of what is known as algebraic geometry codes, which is a wonderful class of codes. I remember them fondly. I do similar things, but not quite to this level. Yeah? Oh, actually, I have some minutes. I think I can present another decoder. Yeah. So if you received your 5 tuple without errors, and these are the evaluation points of some polynomial of degree 2, then you can do Lagrange interpolation, yeah, because the first position is -2, the second is -1, and the third is 4. This corresponds to the evaluation of a polynomial in -2, -1, and 4. You can find the unique polynomial which takes those values at those points. Yeah. So, for example, pretty much this, yeah. you take your 5 values of your polynomial, it corresponds to this, and these are pretty much 5 points in a parabola, and you know your original message was 2 plus 4x plus x squared, which corresponds to the message 2, 4, 1. If you have an error, if by some reason the last position is, received as 0, when you look at all parabolas that pass through 3 of these points, it's the parabola given by 2, 4x and x squared, which passes through most points here. Yeah. So therefore you say, since this parabola is the one that passes through most of my points, this is the parabola that corresponds to my code word. There's another trick which one can do, yeah, which is, again, you take 5 points over your favorite finite field. You take a code word corresponding to the evaluation of a polynomial, and you suppose that your received word, this is R, would differ at most one place. In here I put exactly 1, but you can put 1 or 0. If you can find a polynomial q of xy of the form q0 x plus y and q1 of y, where that is not the 0 polynomial, but the degree of q0 is 3 or less, the degree of q1 is 1 or less, and the evaluation of u at alpha I, where these are your evaluation points of the Reed-Solomon code, and Ri, which are the values of your received word, if these things are met, you can just take q1 divided by q0, slap a minus in front of it, and that is your original polynomial, which corresponds to your sent code word. Yeah. So if not too many errors occur, you can, establish some linear equations and actually find your polynomial. So why does this work? It's an awesome combination of, linear algebra and algebra. Since Q0 has degree at most 3, it has 4 undetermined coefficients. Since Q1 has 2, degree 1 or less, and it has 2 undetermined coefficients, and you have 5 conditions where you have Q of alpha 1 and I being 0, you have 5 linear equations on 6 unknowns. So therefore, such a Q is guaranteed to exist because it has more unknowns than equations. But now, do note that if f of x is equal to r, then f of alpha I is equal to ci for at least 4 values. I don't know which, but f of alpha I is equal to ri for at least 4 of these positions. Yeah. So therefore, if you replace y by f of x, it's a polynomial which has at least 4 zeros. Yeah. Those are the values where actually ri is equal to f of alpha I, but q of x and f of x has degree 3 or less. So a polynomial of degree 3 or less that has 3 zeros has to be the 0 polynomial. And the awesome thing about Reed-Solomon codes is that you can always correct up to half the minimum distance errors doing this. I mean, this is an example is chosen precisely for the Reed-Solomon code I defined before, but this works for any K and any D. Sorry, any N and any K. Yeah, will always work. All right. So I have some brief minutes, so I'll just talk quickly about my REU. So this summer, I'm running an REU in Ponce with Dr. Pamela Harris of the University of Wisconsin at Madison. This year, we'll run it for 9 weeks, and we heeded the comments from our participants. So this year, we'll do a combination. We'll do about 6 weeks in Ponce and 2 weeks virtually, and we'll pay about $600 per week for each week you participate. So basically, we have about a 5,400 stipend. Ooh, yeah. Our application is at NSF's website at ETAP. So if you want, you can take a screenshot, and this should also be in the conference's webpage. Yeah. And I'll just describe briefly some of my coding theory projects. Yeah. So one of my projects is Codes from Grassmania. So in here, I'll be flexible with the notion of points. So I'll just take a bunch of matrices of some fixed size over a finite fields. And our functions will just be taking the different minors of a matrix, or the determinant. Oh, we'll take all determinants of all squares of matrices, and we'll just multiply a bunch of them, and those will be our functions. So the thing is, we don't know dimension, we don't know minimum distance, and we certainly don't know decoding. And the reason why we study this is because the things we find here give information on an object called the Grassmannian. So the Grassmannian is the collection of all linear subspaces of dimension L of let's say F to the M. It's a wonderful set. It has loads of structure. You can study it over the complex numbers, the real numbers, finite fields, transcendental extensions of FP. It's a wonderful object with loads of rich structure, and that's why I like it. So I just use coding theory as a way of doing some things in finite geometries. Related to the project, I also have a project known as Schubert-Hermitian-Grassmann codes. Many names, yeah. So in here, our points will be just certain 2 by M matrices over a finite field. They satisfy the following. The 2 row vectors of the matrices have to be independent, and they have to satisfy a polarity, or I mean, just for our purposes, pretend that the dot product of the 2 vectors has to be 0. Yeah. And just in case, they have to, the 2 vectors have to make a matrix of rank. They have to make a matrix of rank 2. Yeah, I did say that already. But there will be some fixed space A, yeah, and the space spanned by the 2 vectors has to have a non-trivial intersection with a given fixed subspace A. So now the functions will be all the 2 by 2 minors on the matrices. And then we want to know length, we want to know dimension, we want to know minimum distance, and we want to know decoding, because we mathematicians have studied many of these things on their own. None of them have studied these conditions together, and they can have some really awesome interplay. And the other thing I like is that these points, they are also vertices of a strongly regular graph. So they also have a combinatorial object which has a rich rigid structure, and it's just something I find it really cool. Yeah. So I have another project, which is classifications of birds and herpetofauna and decoding LDPC codes using ML techniques. So basically, the belief propagation algorithm I presented, that going back and forth in decoding, you can use these new fancy schmancy machine learning techniques to simulate that algorithm. And then basically you simulate a decoder to try to get decoder done faster. Yeah, so basically that brief problem I showed you, it can be attacked with, or it can be solved with current techniques in machine learning and AI, yeah? And I mean, we're in the tropics. I mean, even my REU says tropics in the name. So why don't I kill 2 birds with 1 stone? So one of my projects consists in using machine learning regressors to decode LDPC codes, and then, use those algorithms to classify birds and cookies as well. So, and just to show I'm not kidding, this is a photo of our, let's say, 2024 REU participants, where we actually went into the field so we could learn about more about, cookies and frogs. Yeah. And I believe maybe a member of the audience will recognize him or him and himself in the picture. But I leave you with this. Yeah. All right.
Great. Please join me to thanking Fernando for this wonderful talk.
Thank you. Thank you.
And I think if you have any question, you can ask it now.
Yes. All right. Let me see if I can. Okay. Wow. I have many questions. Wow. Okay. But this is a direct message. All right. Okay. So what are the code? So let's see. So what are the code words? Yeah. Basically, a code word is just a sub collection of the possible messages. Yeah. If you look at the Hamming example where we had where we could put zeros and ones on all the 7 positions, so you would have 2 to the 7 binary tuples, and that's everything that's possible. But your code words are the only 7 tuples which have zeros, which have an even number of ones on each of the circles. So you go from 128 possible 7 tuples from everything, but the ones that have an even number of zeros on each of the 3 circles, you go down to 16. And those are the circles, or those are the tuples which satisfy the 3 linear equations I put in one of the slides. All right.
So has somebody raised their hand?
Somebody raised their hand. So Simon?
Yeah, I think I'm muted.
Yeah. Oh, he's gone. All right. So Ignacio Maravilla has written, would Hessians help with that? Maybe, maybe not. I'm not sure right now what a Hessian is. I would need to check. It might be possible. I'll look into it. Okay. So, and then Minyard has asked, I'm not a graduate student, so I cannot participate in the REU, but I would love to learn more about project number 3. I have a question. Would it be the Coqui part or the LDPC part?
Las dos.
Las dos. Well, okay. Pues, all right. So in the LDPC part, so here's the thing, yeah? So when you have an LDPC code, you're doing self-decision decoding, yeah? Instead of having zeros or ones, you have a probability that something is 0 or 1. So you run your belief, you run your belief propagation algorithm, and you get another vector where you have updated everyone's probabilities. So for each of your received words, you run this several times, and you get another vector of probabilities. So that's the belief propagation algorithm. You use the code such that everyone updates what they think they should be, and you finish. I mean, you say, I'll run this 50 times or so, and you call it a day. And then you say, whoever thinks it's a 1, it's a 1. Whoever thinks it's a 0, it's a 0. And you call it a day. And this actually works pretty well in practice. We don't even know why many of these cases work. So then what you do, since you started from a probability vector, you run your belief propagation algorithm into another belief vector. So you make a function from one probability vector to the other. So these are your input-output pairs for your machine learning algorithm, and just feed those to the machine learning machine, and it will train on it. It will do its unknown black box magic. And then you see, and then you try to see. So it does its magic. It gives you some regressor. I mean, if it does neural networks, it's neural networks. If it's, I mean, whatever it is, yeah. And then you take the regressor and apply it to the actual codes and see how it behaves as the error rate increases. All right. So Ender has asked me, do I have a paper or abstract online? Not online, but send me an email. I have a draft with a student. I can share, let's say, articles from the literature. Okay. But now if you want to classify birds, yeah, so I mean, I like biology and I like ecology. I was very fortunate to be part of an organization in my undergrad where they took us to the field and they had many biologists talk about the importance of it. So one of the things is, yes, Ignacio?
Hey, mucho gusto. So if we want to spend do we have to do half of it virtual, or can we spend the research opportunity all in Ponce?
I mean, so can you be virtual for the research opportunity in whole of it?
No, I mean, do we have to be virtual, or can we stay in Ponce?
I mean, you can stay in Ponce. It's just that our housing situation is really special. Yeah, I mean, I think you could, if you want, I can put you in touch with some previous participants. Or I mean, we don't have student housing per se, so it was a miracle we were able to find student housing close by. So I mean, by the end of 9 weeks, students were really looking forward of going back home. So we decided to shorten that time to 6 weeks. But I mean, if you're really, really keen on staying in Ponce for the full time, when you apply, let me know, and I'll talk with I'll talk with our housing manager and see what we can do for you. Let me
Muchas
read my,
gracias. Muchas gracias.
let me write my email in the chat. So then what to decode birds? So I had some RU participants who were really, really, awesome computer scientists, and they're really keen on applying, classifiers and regressors and these machine learning techniques to wherever they can find. So I said, when you're trying to work in the field, you have to collect lots of data, but you don't really know what to do with it. So I have a colleague who he's Alejandro, and he puts recordings in different parts of the forest so that he can record birds and cookies, and he can study cookie activity. He studies cookie bandwidth. I learned something really awesome. So the Puerto Rican cookie has a very distinct cookie sound. So the call, it's a territory call, and the females don't hear it. And the key is a mating call, and the males don't hear it. That was awesome. So in fact, you can see that, the different animals and cookies, they have to compete for the bandwidth for their communications. So if you want to have an idea on the biodiversity that's available on the island, what's happening if, as climate change increases, or, what would be the impact if you try to run a road through the mountains, then you need tools to figure out how many cookies there are. So one of the things we're trying is that if I have a recording of cookies, can I count how many species are there? because I mean, if you try to count them by sight, they camouflage pretty well. So if you can do it by sound, where they're communicating, you can really figure out the richness of it. But doing that by sound alone is pretty hard. So we're trying to see how so then what some of my REU students did, they did it not for cookies, but for birds. They converted bird sounds into spectrograms, and then they used, I think it was Facebook's image analyzer, and used the spectrograms to differentiate between birds. Yeah, that was awesome. Yeah. But I mean, since it's a similar technique, you have your tuples, either sound tuples or probability tuples. You attack them with your favorite AI machine learning techniques, and you hope you get something nice. What I really did learn is that you really, 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 really need your domain expert. Because for me, it's all zeros and ones. But for my biology friends, they're birds and, things. Proper things. Yeah, it was really fun.
So sorry to cut it off the
That's
discussion
all right.
here. We are actually officially like the end of this session, and we have a
That's
session
fair.
happening right
All
now
right.
about the
Thank you.
panel. So maybe let's thank Fernando again, and
Muchas gracias.
A ustedes. Un placer.
feel free to check out the session that's happening with this experience panel. I will end the session now.